My name is Fabiano. I'm a PhD student, and my area of study is medicine, where ultimately I want to have 3D gravity modeling. And today I want to share a very straightforward piece of work of my thesis. And because of its simplicity, it's good to see how important it is to constrain the data, but also to handle the gravity data uncertainty. So the title of my presentation is the confidence estimation of the Porcupine Destor fault deep angles at depth of few kilometers. So let's just get the okay, yeah. So I'm showing these three articles, three papers that what I'm trying to say is, although interpreted gravity data caused by deep faults is not something new. You can see here on the left is from 1966, on the right is from 1989, and also, but although, however, nowadays people are still trying to improve and get better results from gravity data, and in terms of interpreting data caused by deep faults. And so, how we can get confident estimate from gravity data? So we are well aware of the non-uniqueness problem in any potential field data, actually gravity mag. So we have this non-uniqueness problem, which is we have multiple solutions for the same data. So in order to avoid this, we have to constrain the data. So we have to have control of the depth of the source, the geometry of the source, and the density problem as well. But also we have to handle uncertainties. And just laser point that to be better. Okay, and why it's important? Let's say, for example, if you have two sections and they are cross-cutting like a fault, and we want to compare both. So let's say, as a result, I get, for example, 40 degrees south, or in another section 50 degrees south, but I don't know the uncertainties of these numbers, this angle. So I cannot say, okay, this is I can compare like the fault angle, say, okay, it's getting lower as I'm going that direction. So we have to, we can get more confident estimation. So the overall objective of this piece of work for my thesis is determine the Porcupine Destor fault deep angles, but also provide error bounds in three section Madison area, and by computing a ground forward gravity modeling. So here we have the geological map of the area. So it's quite diverse in Madison area, but we'll be focused on in this smaller area. So we have this metasedimentary rock here in gray, which is the Porcupine assemblage. And also we're gonna be focused on the MAFE intermediate metavolcanic lower Tisdale, which is this part you can see on right in this map, a little bit simplified. The Porcupine Destor fault all the way crossing here in red. And we have the Porcupine assemblage on the north and the lower Tisdale at south of the Porcupine Destor fault. So we have these three sections, B, C, and D, Volga, what a big Madison. And the distance between B and C is pretty much the same from distance between C and D, which is about 7 kilometers. So this is the gravity map, complete Boolean map, anomaly map, and but just by take a look, we can pretty much can see this negative anomaly in the gravity map, and it's very easy to associate with the Porcupine assemblage, which is in gray. So the Porcupine Destor fault. Actually, the reason why we can estimate deep angles of this fault is because we have at north the Porcupine assemblage, as I mentioned before, which here we have the density property associated with this assemblage, so it's 2.73 grams per cubic centimeter, and at the south of the Porcupine Destor fault, we have the lower Teasdale assemblage, which is a reasonable higher than the Porcupine assemblage, which is 2.89 grams per cubic centimeter. So because of this density contrast and the contact between these two assemblages coincides to the fault, we can estimate the Porcupine Destor fault itself. So, and economically, the Porcupine Destor fault is very important because several deposits have been associated with gold deposits associated with this fault. So here again we have just to emphasize the gravity map, and also all the way the Porcupine Destor fault in this. So which is very easy to to associate the Porcupine assemblage in the gravity map. So in previous studies, they have suggested that the Porcupine Destor fault is deep in south, for example, in this seismic interpretation, and also others. These other two also are gravity modeling, and they are suggesting that the Madison area, at least the Porcupine Destor fault is deep in south. So we can see it from here south. All of this section, we are looking west, so they are the same in terms of direction. And as you can see, they are suggesting that deep in south, and it is important for us at this point because we have to decide which gravity station we have to use in order to estimate the fault. So although the area, there is a good coverage of metal earth, blue metal earth gravity stations, and also the government compilation in green, but because we don't know the uncertainties and we are not able to estimate the uncertainties for the government compilation, we can only just use the metal earth station which are in blue. So, and because they are deep in south, the gravity station that gonna have more effect because of the fault, not because of the fault itself, but because the Porcupine assemblage will be south, at south of the for the fault. So on the right, sorry, we have just the data that we use it for create the models. So the section B, C, and D, as we can see, south it's from this direction, and north on the right. So as we approach to the Porcupine assemblage, it's okay. The measurements become smaller, so it makes sense because the density of this assemblage is much lower, as we already mentioned. So, and in terms of the gravity, metal earth gravity data, so the spacing, the average spacing about 300 meters. And we use it Syntrex CG6 autograph as a gravity meter, and for elevation and position Trimble R2 GNS receivers. And in this map in the middle, it's the gravity stations that we use overlaying the geological map. As I mentioned before, they are either close to the fault or located at south of the fault. And as I mentioned before, the ultimate goal is to have like a forward model. So the forward modeling is very straightforward. So we have in this panel, the top. So the dots are the data that we acquired, the observed data. So, and we create a model either using any constraint that we have, or if you don't have, we just have a model. And based on this model, we generate a predictive model, which a predictive data based on the model, which is the dot lines here. So the goal is to get a lower misfit as low as possible, and the misfit will be the difference between the observed and the predicted data. So and here is the model. So let's say if by changing this angle of the fault, we're gonna have difference in misfit. So the angle that we get, which have the lowest misfit, will be more likely to be the angle of the fault. But in this, as I mentioned before, you have to handle all of these variables, because otherwise any model can explain this data. So we have the density problem, the source location, the source geometry, and the data uncertainty. So we have to take account all of these variables in order to have like a confident model. So the first problem that we have is the density problem, but we could solve this by either compiling data from previous surveys, or we also have to took samples and estimate. So for the Porcupine assemblage, we had 46 dense samples, and for lower Tisdale assemblage, 90 density samples. So as I mentioned before, here are the average density for lower Tisdale and for Porcupine. So now we have the density problem over control, so we just can move on for like the source and geometry location. So we could benefit from Meta-Earth high resolution seismic section, which you can see on the left for the Volga section B, C, Waterbeek, and section D, Madsen. However, we can actually only see the reflectors that was interpreted as the bottom of Porcupine assemblage, which, as previous studies suggest, the lower Tisdale is also underneath of the Porcupine assemblage. So we could, at least by using seismic data, fix the bottom of the Porcupine assemblage. So let's say the location, because we also have the surface geological map. So the location, it's resolved, let's say that way. But the source geometry, we really cannot see any reflector related to the Porcupine Destor fault. And the way that we had to do is make assumption that the fault is linear. Okay, so it's the reason why the check mark like is in red. And also the 2D modeling, we are assuming that the fault, in this case, the fault has like an infinity strike length. So it means that the fault is perpendicular to the section. That's, for this case, really is quite not that bad in terms of making this assumption, because the fault is pretty much perpendicular to the sections. Okay, so we can move on from the data uncertainty. So now we have to handle the data uncertainty and take into the model and see how sensitive the model can be based on the data uncertainty. So we actually estimate the gravity data uncertainty using two methods. The first methodology was we actually designed the survey that way to have repeat measurements, and about 10% of the measurement was do more than once. So some gravity station, you can see this is the Meta-Earth gravity stations on Madsen area. So in green are all of the gravity station, but those in blue are the repeat ones. So we could use these repeat measurements and estimate the error of this survey for the data that we use in the model. So for using the repeat measurements, so we got 0.109 milligauss, and because you are proposing and using a more straightforward method, which was just compare the repeat measurements, we also use a more larger used one, at least in physics, which is the Air Propagation Equation, where you take account all of the variables in your measurement, you are correcting the data, or either correcting data or reducing the data. So, and this one take account all of the variables. So it's and it makes sense to be a little bit higher, but really they are not that different. So it's just a little bit higher, 0.12 well, 1 milligauss. And now we have the data uncertainty of this survey, but we have to take it into the model. And the way that we found out to do that was by contaminate the data with random noise, and this random noise is based on the Gaussian distribution, and also use the uncertainty that we just got from our estimation, so 0.121. And when you say contaminate the data, you say the word noise, it seems like a bad thing, but what we're trying to do here is like, okay, let's say if you go to the field and acquire this data again using the same equipment, how close you'll be my data, like today and tomorrow, and every day that I acquire this data, how close you'll be. So, and by contaminating this data based on the data uncertainty, we can do that, and we don't need to go to the field. So we just can estimate how reliable is our data. So, and okay, and we have all of this noise data set, and for every noise data set, we're going to create a model, and this model will be constrained using scientific data, using geological map, and any information that we had. So let's say just take a look in this the first one, in the first panel here on the top, we have the observed plus noise 1, right? So just for this model, we got, for example, in this case, 43 degrees south for the fault. And by getting the other noise data set using another randomly noise, so we got about 45, and again 47. So by doing this, like these three examples, we kind of have idea how sensitive is the fault, the deep fault estimation based on the gravity data. So it's, for example, in this case, we start from 43 and goes 47, so something like that. But the thing is, it's for the Madison section D only. And the thing is, how many times you have to do that, because it's time consuming. Every data set that we introduce noise, we have to calculate the fault, the depth of the fault. So we actually do that until like our average for the fault and also the standard deviation doesn't change anymore. So for example, for the section B, we have to do 30, you got 30 models. And based on the average of that 30 models, its default is about 28 actually degrees, and uncertainty is about 1 degrees. So, and for this for the section C, what a big line or section, we actually only 24, and for Madison line, 23. So as you can see here, pretty much it is Gaussian distribution. So it makes sense that at some point forward, it doesn't change anymore. So, and by doing that, we could get like as a final result, all of these angles for the fault deep in south. So 28, 54, 28 plus 1, 54 minus plus 1, and for the Madison transect, 45 minus plus 2. And here we have as a result emphasize the uncertainties, and also there is no vertical exaggeration here. So we have final model for 3 sections, and we have control of the density problem, source location, source geometry at some point, and data uncertainties. And in terms of more like a 3D view of this fault, we can pretty much see bit comparison C and D. They are very close in terms of how deep, how is like the fault is deeping. But as we go towards west at Vaughan line section, so it's much lower the angle. So it's 28. It's more like a geological results from this this modeling. And as I mentioned at the beginning, so it would be important because now we know, like we can say, okay, this is different than this, because like the uncertainty is, if I take into account, it still will be very different, let's say B and C, right? If I didn't have these error bounds, I don't know, can be different, but because I don't know the uncertainty, I cannot affirm that. And okay, as we can see here in orange is the uncertainty of the dip angle, and they can say, okay, it's negligible, right? So, but let's say if you have a data with larger uncertainty. Here, for example, is the same data. However, the noise that was contaminated was about 1 milligauss. The same model, the same data. We have size data. We constrain the bottom. We constrain the density. We have the surface geology map. However, like when we try to get the uncertainty of this fault using this fault dip angle using a large uncertainty, we're going to have, for example, 27, 66, and as a final result, we're going to have 45. It will be the same because we are using the same data, but the uncertainty will be much larger, and it really you cannot help you have an angle like a 45 minus plus minus 41, right? So it's doesn't help too much. And by the way, for 1 milligauss, when we don't have uncertainty, it's the standard. For example, for all of this compilation, maybe you have data as good as Metalworth, but because we don't know, we just assume that's 1 milligauss, and doesn't help too much. And maybe you also have data that 1 milligauss that does compilation. So, and just for comparison, I have a data, Metalworth data 0.12 milligauss, and I just make 8 times bigger, right? About 8 times bigger, 1 milligauss. But it's only 8 times bigger, but the uncertainty of the fault is about 10 times higher. So it's emphasized how important to have a good data, at least a good gravity data, in order to have a more confident model. And as a conclusion, so we are able to obtain fault dip angles with confidence by hand uncertainties and constrain the models. And the fault dip, more geological results, the fault dip has much lower angles towards the west, as we could see in the final results. And also something that's very remarkable, the Metalworth data is very good in terms of accuracy and precision, as we could see in this piece of work. And gravity data compilation, it's something that I'm always advocating. So gravity data compilations or any gravity survey should also provide uncertainties, or at least provide uncertainties of relate to elevations and gravity readings. In that way, we can estimate the overall uncertainty. So it's enhance a lot of data. So yeah, it's pretty much that I have. I'll be happy if you have any question or suggestions.
Great, thanks very much, Fabiano. We do have time for questions.
Yeah, I have a question, Chris here.
Yeah, go ahead, Chris.
Yeah, I was wondering, did the base of the Porcupine unit, did you assume that that was 2D or 3D in this method?
Yes, 2D, always was 2D.
Yeah,
like
but the size, yeah, but the seismic shows that it's 3D.
Is in this or this section?
Yeah, if the seismic section is there, the depth to that green line.
Okay, yeah. When you are comparing, like comparing different sections, because they are in. Okay, I go. Yeah. So the assumption is 2D. Okay, and there is uncertainty also associated with this assumption. And if you, for example, take a look in this this example, this is the Madison line, and if you take a look in the misfit, right, in the best angle, okay, 45 degrees, the best angle, the misfit is about 0.50 milligauss. So it's not that high, right? So I mean, this misfit is pretty much because of the 2D modeling assumption is not 100% true, it's right, and also because of assuming the fault is linear. But even I'm doing this assumption because like the remain misfit is still low, is still, you know, it is still okay in doing that, right?
Okay, but for each line, you're assuming a different geometry for the base. Is that right?
Yeah.
Yeah. Okay. Mm. Okay. Thank you.
No problem. Yeah.
Any other questions?
Yeah, Fabiano, it's Bruno. Can you go to other parts of the Porcupine Destor where you don't have a seismic section and estimate the dip of the Porcupine Destor? Because
Yeah.
it's interesting, those changes are in dip or would be the equivalent of jog or relay zone along the fault. And that could be well controlled, and that could be an hypothesis for controlling gold mineralization, having the change, the jog, the change in dip in the Porcupine Destor. So I wonder, can you apply that to where you don't have the seismic section?
Yeah, it's something that actually I have talked to Gaetan to do at the Timmins line. But the thing is, if I don't have seismic, the problem will be the bottom of Porcupine. So that the uncertainty of the fault will be much higher in that case. But we can estimate. But you know, maybe you have like, for example, I don't know, but in a place that you don't have seismic and you have like, let's say 40 degrees and the other section 50 degrees, but the uncertainty is like plus minus 10, you know, and doesn't help, you know. So, but yeah, we could try. I guess it's a good idea to do that.
Anyone else? All right. Well, thank you very much, Fabiano.